presentation on solar PV. I have been pushing this one pretty hard because I can anticipate that there are problems with solar PV as the amount of it increases in our network and just spills into the network in a fairly uncontrolled area. Okay, so I'm going to take you through a few slides on about Western Power, our solar PV analytics, and just give you some motivation about why this demonstration. Then I'll hand over to Nick Angerer from Solcast. Nick there. Nick's a professor of engineering, I believe.
Close enough.
Cool. And has developed some very fancy algorithms to actually track and calculate how much solar energy is coming out of into our network, or at least generated within the footprint of our network. And then from there we can actually calculate how much we think is coming into the network. Then following Nick, we'll have a presentation on actually how you set up a cloud analytics system. This is something that was a non-trivial exercise for me as that analytics manager here at Western Power. Is, okay, I can see this cool stuff being developed. It actually addresses a key blind spot that I think Western Power has and many other distribution service providers have. How do we get it into our systems? And so Andrew will take you through that. And then there'll be a Q&A session after that. Hopefully we'll stay on time. So the schedule, quick introduction and then hand over. So about Western Power, how many people are not from Western Power in the audience today? Cool, so these slides are for you. But hopefully I think given the audience, you probably already know that Western Power builds, maintains and operates the transmission and distribution assets for the Southwest Interconnected System. So the orange coloured area of the map indicates the network footprint. So we've got solar PV largely concentrated in that area. We have about 224,000, probably pushing closer to 230,000 since October last year, and at least 220 battery systems. So these are just estimates, but we know we've got a lot. What do? Well, we transport electricity from generators to end consumers. Our customers are at the centre and the reason why we exist in the network, supplying power. But we know now that a lot of those end customers are actually also producers. And so we live in an exciting time when the entire industry is actually transforming quite radically. So that, because of this radical transformation that's underway, set off by deregulation and then solar PV that's coming in, connecting to our grid, and many new things that will happen in the future, Western Power is now exploring the best way to maintain the network in the future. So whether we remain an integrated network on the left, or we have fringe disconnections because small-scale renewable generation coupled with other technology can be quite effective at supplying power for isolated places. So how far down this disintegration we go, we're not entirely sure yet, but there are a number of scenarios presented there. And so I know that many people in Western Power are busy working out what this future actually looks like. So why this demonstration? Well, we've been seeing some media interest in recent weeks about the amount of solar PV that's now connected to our network and spilling electricity in an uncontrolled way into the network. So we have power system engineers that keep saying that PV presents risks to supplying reliable power. And that's a call to action to do something. Some of them remember the bad things that happened when air conditioning load grew beyond what the network was designed to actually deliver. When the risks finally materialised, a lot of money needed to be spent in a short time frame. And now that we're in a much more of a market environment with a lot of competing technology, that's something you don't want to set off. It's already been set off to some degree, but there's still the chance that we can actually control it and guide it. If we had better analytics, most of those problems would have been avoided. So today is really about giving you visibility of what's going on in the network. Now, a lot of this is actually happening in the distribution network where there isn't a great deal of visibility. The good news is we have reliable power now, so all the good work that's been done over the last 5 to 10 years has placed us in a very good position. We want to keep it that way. We also want to make sure that it's done in a highly capital efficient way. So how many of you in the room are economists? There's a few. Excellent. So this is for the economists. So we know we need to do something, but what's the most efficient way of doing it? Traditional ways, maybe without proper visibility, may be extremely expensive solutions. So we need to only spend the money where it's absolutely needed. And our task is to identify where the problems are emerging and correctly anticipate where and when other problems will appear. So what you'll see today is very much about that, about giving you the visibility at a very granular level. So we already have Solcast estimates at the zone substation level. Stage 2 is really proposing to go into the provide the visibility to the low voltage networks. So once we've got that in place, how can we spot problems? Spotting subtle anomalies before, so there's one message you get out of today, it's little rocks and big rocks. So big rocks are easy to spot right before they cross you. But little rocks are much harder to spot. So given the number of low voltage networks, it's not just practical to manually search for them. And we have other issues anyway. So we don't have adequate metering data yet, but it's coming. And our SCADA data, as comprehensive as it is at the transmission level, is actually very complex. And it's increasingly difficult to actually untangle what these highly dynamic electrical processes are doing. So we need to search very efficiently. What you'll see today is a step towards an elegant and practical solution to the problem of scanning for subtle anomalies. Solcast and Perfect demonstrate what can be done to develop a good measure of solar PV generated electricity. We can use this to identify network problems through the application of statistical and engineering based methods. We can also identify problems that are not related to solar PV, and this helps us target the right problems with the right solutions. So I'll reiterate again, this is not just about addressing the problems, but addressing them in a capital efficient way. We can scale the solution that you'll see today. There's a clear capital efficiency benefit if we do. We'll be able to pinpoint where there are problems before they are big. We can ramp up the scale of meter and sensor deployment more slowly, and we can minimise the capital expenditure required to keep the system reliable. And in case it's not obvious, since that capital expenditure is passed on to our customers, that's prices that won't go up as a result of doing something a little smarter. So finally, before I hand over to Nick, just a quick reminder, what you're about to see is a quick review of the Solcast data services, an outline of the use cases across the 12 partner distribution network service providers through the Australian National University led by this ARENA funded project. And Perfect will then show you how you actually ingest that information in a meaningful and useful way that presents meaningful diagnostic analytics to people who need to understand what's going on. So with that, I'll now hand over to Nick Engerer, please.
Thanks for that, Grant. I think the last time I was here was April 2016, and I sat out there in that lobby with you, Grant, and this was all just a big idea, and here we are. I'd like to say and just make a note that this takes leadership, what Grant's doing, setting this up, getting the team in here, inviting so many different people to talk about this, and I commend you for that, Grant. Thank you. And it also takes a bit of forward thinking to invite organizations like the Australian National University, Soulcast, Perfect, Weather Zone, to all come in here and engage a very difficult and challenging problem, and that's what we're doing today. So I actually put a mugshot of myself up there in case people on the internet weren't able to see the video, so they know what I look like. I'm a friendly guy. I'd love to shake your hand and have a drink sometime. If you're out there on the webinar, and everybody in this room, obviously you can prove that I am who I say I am, I guess. I mean, I did put that in front of you. I could be lying. I am here today in my role as a lecturer at the Australian National University, where I built solar radiation modeling and forecasting tools and PV analytics tools for distributed solar in my PhD work. Came to Australia, saw a big challenge, big opportunity. It's been a great experience for me. I call Australia home now, permanent resident, sticking around. It's a beautiful place to live. It's great. My 4-year-old son loves it. And I actually won some funding from the Australian Renewable Energy Agency to take that work in my PhD and effectively operationalize it. And that was distributed solar tools I had built with Act2AGL, now Evo Energy, and basically put up to a prototype in the cloud and was able to show to ARENA, hey, I think that our networks are going to need something like this in the future, and here we are. And as a part of that process, I co-founded the company Soulcast with my co-founder James Luffman, because I found he had started working on some of the satellite algorithms and forecasting tools that our project in the ARENA effort actually was going to build. And so we actually came together and formed Soulcast at approximately the same time we started this project. Now that's made things very interesting, because I thought I'd form Soulcast at the end of this project, and now we've actually had an arrangement where we work together. And I'd like to talk to you about that today. So I've got a few pictures of my amazing team up here. I couldn't be doing any of this without them. I have one of those team members here with me. It's Pia. Put your hand up, wave hi. And also Josh from Weather Zone. And we collaborate on this ARENA project to interact with the DNSPs. And you'll also see some collaboration from Perfect later in the talk. So the project that we have is a $4 million total project, a little over $1 million from ARENA. Effectively to take solar data tools and deploy them to distribution networks. And our goal is to enable higher penetrations of solar in those networks. And as you'll see here is it the SWIN now? It used to be the Swiss. Is it the SWIN? If I get that right. We have high penetrations of solar. And that we're starting to see we need to think about how to enable these higher penetrations. And our current focus in the project, we're now wrapping up the second year of the project. We've been talking with the distribution networks and figuring out where can we use this data and how. Because, unbeknownst to probably most of you in this room, low voltage network operators don't actually know how to use solar forecasts or solar historical data to a large extent. So this is actually a learning process, and the ARENA project is ultimately looking for those use cases. And we're exploring them and establishing pilot projects with each of the participating networks. And our end goal is to take those use cases and integrate the tools in a way that is useful for those networks at the end of the project. And this is really important. When we look at the penetrations of solar in Australia, they're extraordinary. When we look at the installation rates, around 600 gigawatts 2016, 1.5 gigawatts in 2017. We'll do 3 gigawatts of rooftop solar this year, add another 3 gigawatts of large solar. We're going to break the renewable energy target, and this is going to keep going because we see that it's a different segment of the market adding solar now. It's the commercial segment, large rooftop segment, adding the solar, and it makes total business sense for them while the residential space remains strong. And that is because solar is an exponential technology. What do I mean by that? I mean that it is cumulative capacity over time, grows in a straight line on a log plot. It's approximately doubling every year. When we look at the cost and volume, so total shipments versus the price, we see, again, downward slope on a log plot. So everybody who's forecasting how much solar will be installed, different forecasting than what I call forecasting, over the next several years, is wrong. And they'll continue to be wrong until they realize this. And so this is not a problem that's going away. It's significant. It will continue the pressure, and particularly with those large solar farms coming into the national electricity market. We're headed for unprecedented, uncharted territory. So forward thinking, looking for those little rocks and figuring out where these problems are starting to show up is really smart. And you'll see from our presentation from Perfect later, by collaborating with them, we've been able to start to see that. So our objectives in this project, our big objective is to give solar PV visibility to DNSPs like Western Power. How can we help them see what's happening with solar in their network in the past, now, in the near-term future. And so what we do is we partner with each of these 12 DNSPs to get them to provide us comprehensive network data where we know the installation of PV systems, the locations, the capacities, and how that maps back to the network hierarchy. And this allows us to actually build forecasts and estimates of historical power production according to the network itself. So for entities like a system operator like AEMO, we can largely know the broad market regions that solar generation is occurring on, and that can help us balance supply and demand. When you look at a low voltage network, you need to understand what's happening on a given feeder behind a different distribution transformer associated with its own substation in order to know how to design solutions to deal with solar intermittency and the various other problems that solar can cause. And so this is a very simple idea of what we do. Getting installation of PV systems, knowing where they're located. They're behind a meter here. Transformer, feeder, zone substation. I made this in PowerPoint. I hope it impresses you because that wasn't easy. I know it's a little bit, not quite electrically accurate, but it gets the point across, right? And we're able to see where the solar is, how it will map its power production back to the various aspects of the network. Another way we're establishing solar PV visibility is we're actually getting actuals in from the solar PV systems themselves. So this means that we're monitoring through data provider partners the actual performance of PV systems. And I'll show you some examples of that coming up. And this allows us to run some analytics on this data in order to infer some of the properties about those PV systems and see how well the tools that we're deploying operate. And so this is an example of South Australia. This is data coming in from a data provider, Fronius, and also some sites from pvoutput.org. Gives us really comprehensive coverage across the broader Adelaide region, but also fairly good coverage throughout South Australia of what PV systems are actually doing. And that helps us understand cloud cover conditions and use these PV systems as reference sites. Our goal, we've started in South Australia with Fronius for obvious reasons. We're scaling to WA next, but the ultimate goal is to have tens of thousands of these points across Australia so we can have a very comprehensive picture of how solar is performing and also match that up with the satellite modeling that we get from Solcast. So this is effectively how this works. This is the big flow diagram. I'm going to walk you through this. We have a solar forecasting engine that produces estimates of solar radiation. We have some PV power modeling algorithms that can use those radiation forecasts to make a prediction of PV power output. And then we have an API service that does all that grouping by the feeder and the zone substations and delivers the data back to the end user. And so this top part, that is what we get from the entity Solcast. That's what it does. Creates the estimated actuals, creates the forecast, has the API service. But this is not good enough by itself for low voltage networks. We actually have to add bringing in granular PV data organized by the networks. This data is in tough places. It's sometimes incomplete. It needs to be updated regularly. There's all sorts of processes that are needed to pull that data out from a network service provider and get it matched up to this system. So we actually bring this stuff all into a database. We're establishing a way for that data to be uploaded automatically to our systems in the cloud, and so that we can keep it current. And there's also the question of how do we get this data back to DNSPs in a useful format. Grant mentioned that earlier in his talk. That's precisely the demonstration we'll see from Perfect later today. I'm going to briefly explain what Solcast does. I'm not here in that role today, but it is important for us to understand. So Solcast is a standalone company, a fully commercial company, and it offers forecasting solutions minutes, hours, days ahead, all around the world, and also builds a history of the estimated actuals. And it does that through third-generation weather satellites. This is very high resolution, very granular data coming from satellites like the Himawari 8 satellite over Australia and eastern part of Asia, or the GOES 16 satellite over North and South America, just here on the right. And so this third-generation weather satellite data, we're talking 10 to 15-minute scan updates, 1 kilometer resolution imagery of the clouds. It's very high fidelity data, and it enables us to ultimately model down into the low voltage networks what's happening with solar and produce some very excellent forecasts. So this is an example of some forecasting from Solcast in South Australia. Observed cloud opacity on the left a ensemble-based forecast here on the right. You'll see that this is updating every 10 minutes with each satellite scan. And over here, you'll see that this forecast goes out to goes out to 2 hours ahead in this image. And so these satellite forecasts are updating every satellite scan, new forecast. And not just one forecast, an ensemble of forecasts. Many different deterministic forecasts to create a probabilistic forecast in the end. And I'll show you an example of that from our neck of the woods shortly after this one. And so the products that are available from Solcast end up being tuned PV power forecasts, meaning the forecast for rooftop solar sites. Tuned meaning that we get data sent back from the solar sites to improve the forecasts. Network aggregations, this would be doing an entire market zone, an entire region of forecasting for rooftop solar. Forecasting for solar farms down to even just minutes ahead, including sky imager tools. And the radiation and cloud covered data that ends up really being the fundamental data that allows engineers and other folks to build their own tools or to run their own tools more efficiently. And so that's a really brief picture of what Solcast does. And if there's any follow-up questions on that, I'd be very happy for you to send us an email in that role, but I'm going to get back to what the ANU project does. So that's a brief of the technology that we're able to hook into to deliver these tools to the distribution networks. And then what I want to focus on for the rest of the talk is this part down here. How do we actually take this data from DNSPs, organize it into a useful format, and give it back to them in a way that they can use it? So this is pretty interesting. This is actually, I guess it's the SWIN, but this is some cloud nowcasting here. This is Perth, and we're looking at observed cloud opacity here on the left and a forecast here on the right. This is just one forecast member, and we're taking these clouds and we're forecasting their future position in space and time. And this is pretty interesting. This is just from last week. You can see we do a pretty good job of timing the arrival of this cloud even an hour and a half ahead of time. And again, this forecast updating every satellite scan every 10 minutes. And then we also have an ensemble-based forecast. So this is, you can see, there's a bit fuzzier image here for the forecast because it's looking at when some of those little rocks might fly at us. And also building a historical data set based on the actual satellite data, be able to look back in time and do analytics. So this is an example of, and I apologize, it's a bit bright in the front here. We could share these slides with the audience later. But this is, you can't see the difference between the two lines, but that's ultimately a good problem. The estimated actual performance of the entire Southwest Intercadet network, is that it? Yeah. With the 1 hour ahead forecast plotted against it. And so we can see that with this type of technology, we can actually have really strong confidence in most situations. I say most because thunderstorms can often surprise us a bit if they happen quickly enough for 1 or 2 hours ahead. But this is updating every 10 minutes again. So we can get a very good understanding of what's happening now, what's happened in the past, and what will happen in the near-term future at the whole network level. And so I actually have a little mouse over here. I forgot that I was animating there. And so these demos, if anybody would like to take a look at them, we can, in terms of if you have some use cases for it at Western Power or AEMO, for example, we can let you guys take a look at this data. This data is in an API, and I'll show you how that works just shortly coming up here. All right, so one of the things that we did with this project is we took that capability and we took it all the way down into the low voltage network level. So this is with the Western Power data. We have built an API that allows the user to pull data at the zone substation level. And so we have that very granular information about where the solar is installed and how it's actually connected back to the network. So we know how much solar is effectively being generated. I'm going to call it behind the zone substation. So what this allows us to do is then put this data into an API where a list of all the zone substations is available to pull that data from. And do you remember how many this is, Grant? Do you remember how many are there?
I think it's about over 100.
Yeah, over 100. That's the right number. I know it's over 100. And behind, for each of these zone substations, you can go in and pull out the data. So this data here is actually showing us a recent forecast at the Albany zone substation. This is just a demo chart where the forward-looking line here with the shading around this gives us that probability band. So this would be the satellite forecasting horizon out through weather models looking a day ahead, and the satellite scans building a history back over time. That data actually all sits behind the API layer. So this is all actually retrieved in a web browser. So if you know this URL, you can get this data, and you can also download it in CSV, XML, JSON, JSV, many different formats. And so this allows anybody at Western Power can go download data from any of these zone substations, looking back at the estimated actuals, looking at the current forecast, and ultimately for the IT people in the room, you know how APIs work. You can build this into a query or some scripting that runs automatically and pulls this data in, perhaps at the end of the week, perhaps every day, perhaps every new satellite scan time step, depending what your use case for it is. This is why the API is so powerful, because it allows that flexibility. So this is all built with the satellite-based product. So the satellite stuff we saw from Solcast earlier. So estimated actuals looking back, forecasts looking forward in the future. The interesting thing that we're working on now is we're actually also bringing the PV actuals that I talked about earlier in through the API as well. So APIs aren't just one way. When we go and grab data from an API, we call that a GET request. But APIs can also accept a POST, which means that you send data to the API. And that's actually what we're doing at scale with these solar PV sites that I was talking about earlier, the PV actuals data. And so we've just rolled this out to Evo Energy and the ACT. We'll be giving this to SA Power Networks and Western Power next. It's a little dashboard that will allow them to see the performance of PV systems in any part of their network, based directly on top of the satellite-based system. And then we have the 1 hour ahead forecast, again based off the satellite-based forecasting, but then also the actual performance of the PV system in there as well. So again, one of the things we found we need to do with DNSPs to make them confident in this data and use it to operate their network is need to show them that they can trust it, that it has validity, that it's accurate. And the interesting question about accuracy, I love the question about accuracy. As a forecasting person, I always get asked, oh, how accurate are you? Everybody wants a different answer. They want a different metric, they want a different time scale, they want a different horizon, they want a different region, they want a different way of explaining it or displaying it to them. So ultimately, this data sits in the API, you can pull it down, and you can calculate whatever you'd like. And ultimately, I think that the most important thing is the emotional connection you get to seeing, well, hey, the satellite forecast says the PV was going to ramp up, and then it did. Or it says it was going to ramp down, and then it did. Or wait a second, looks like it missed this one. I'm going to type Nick an email and ask him why his forecast is so junk. Right? And it encourages that dialogue to happen. The other thing that's really interesting about the PV actuals data is it allows us to improve the forecasting and modeling overall. So one of the really interesting things about the partnership with the ANU working with Solcast is that at the ANU, I've got a team of postdocs and PhD students and honors students where we're building algorithms. And so we actually have algorithms that can look at the PV actuals data. And this is over time, a couple years here, calculate degradation rates in the PV data. We can detect shading events in PV systems. So we also can validate that with some LiDAR data and say, yep, we detected a shade event, looked at this PV system on Google Maps, got some LiDAR data, yep, there's some trees there. That's really shading. And actually the analytics that we can run on understanding what shading is occurring, you can imagine once you have 1,000, 10,000 PV systems, you can start to get representative statistics how much shading is in a given part of the network or energy market zone. The other thing we can do is we can infer the azimuths and tilts of PV systems through this data, this PV actuals data coming in. And unsurprisingly, we end up seeing that azimuths, meaning the orientation east to west of the PV systems, tend to be fairly Gaussian in their distribution when you get to statistically significant numbers. And that's just meaning that you have a mean value and a standard deviation that's pretty well behaved. Similarly with the tilt angles, although you end up seeing a lot of weird roofs, sometimes things are flat, so that one's not quite as clean. But this actually becomes really important data in terms of making better estimated actuals for a given part of the network, better forecasts for an individual part of the network. But I think most excitingly, bringing this data in real time can actually help us make better forecasts. One of the most challenging parts of cloud nowcasting, short-term cloud forecasting, is that clouds change their properties fairly quickly. On a day like today, we were walking into Western Power, you could see cumulus and cumulonimbus clouds growing and shrinking and dissipating. And so those challenges are very real in the forecasting horizon. And that's a difficulty, but also knowing the actual opacity of clouds, how much light is making it through clouds, is very difficult. One thing that people don't necessarily understand is that a satellite image doesn't tell you anything about the surface solar radiation. It only sees radiation coming back to the satellite. The visible light spectrum, the infrared light spectrum coming back from the Earth. So understanding the solar radiation making it through the clouds is a challenge. But if we have enough solar PV systems, we've actually published a paper in the Progress in Solar Energy journal last year where we showed if we bring in PV data, this is in Canberra, we can actually start to see where the satellite's missing some things or where clouds are thicker or thinner than we thought they were. And with enough PV actuals data coming in near real time, we can ultimately make a better forecast, produce a better estimated actual. So that's something that we're going to be moving into operations over the last course of the year of this project. And again, that represents the power of collaborating with world-class research with a technical entity that can commercialize and operationalize the product. And so if I stand up here having to wear two hats, that can be a bit awkward at sometimes. It can make certain people a bit uncomfortable, but ultimately we're trying something new here. And from the perspective 2 years in, it looks pretty promising. Looks like we're ending up with some pretty good results. And this is the coverage that we have in WA at present. So this is something that is readily available out here. You can see as you get down into the more dense parts of the urban regions of around Perth, we have really good coverage. It's a little bit more sparse out in the regional areas of Western Australia, but this data will allow us to be creating better forecasts in WA in the very near future. It will also be the type of data that will be coming through in that dashboard to the DNSPs in Western Power, or the engineers in Western Power, to download some of that data like I discussed earlier. And we'll be scaling that up hopefully to thousands of PV systems over the course of the next year. Now, one of the things that we've done at ANU, and I've done as the chief investigator on this project, is I have traveled around and had the opportunity to meet with every single DNSP in Australia. And by doing that, I see the immensity of the challenge that's before us. And we quickly realize this can't just be something we do ourselves and end up expecting to make a big difference. We have to find people to partner with us. And so that API, that zone substation API, ultimately for an R&D purpose or to help develop some commercial solutions, we will share that with anyone who'd like to see it, as long as we can determine that it's going to be used in a way that creates values for the distribution networks. We will share that data. And that integration step, the pulling the data from the API and getting it in front of engineers, analysts, operational services in distribution networks, is not a straightforward task. It's fairly bespoke in that many different systems exist in each of these network service providers, and the way data comes into them, into their historian, into their IT systems, is widely varying. So this is a big challenge. And one of the great things that happened by working with Western Power is that Grant was able to help establish a relationship with Perfect, who's now going to give you a demonstration of how this data can be used to create insight for Western Power. And that is what we need to be doing. And I would say that we're going to have a great use case here with Perfect they're going to show you, but we could easily come up with more ideas than that, and I'd be very, very keen to follow up with individual ideas from this webinar, from those of you in the room, those of you on the web, about what we could do with this that solves other problems or addresses other parts of the network challenges of integrating solar, because there's many of them out there. We're going to be demonstrating the technology through a pilot project at the Waikiki Zone Substation. And where's that located, Grant?
Just east of Rockingham.
So east of Rockingham, and on this zone substation, there's how much solar installed? I forgot to put that in the slide.
A lot.
Yeah, there's a lot. It's one of the higher penetration regions.
The reason why we picked on Waikiki is it's one of the zone substation areas where we are actually seeing reverse flows to the substation.
Right, so we're seeing reverse flow through the substation. That sounds surprising enough. There's reverse flow up the transmission network in South Australia from rooftop solar. So significant challenges again, very relevant. And so Western Power, through the ANU-led ARENA project, has provided the PV installation data. We were given 10 years of historical radiation data to produce PV power output estimates from Solcast. We have 11 years of historical weather data provided through historical weather zone data, and then this data was all pulled together from many different angles in by Perfect to help draw some insights. And so this is an example of how the forecasting has gone over the past week. At Waikiki, again, 1 hour ahead forecast accuracy displayed there. One of the more interesting parts is catching a ramp like this, ramping up positively. And then, of course, we have the chance to look at some of the satellite data. So meteorologically, what we have here is a cold front approaching, convective storms initiating along this cold front. This imagery is actually a little bit old, so if I do a refresh on this, should be a Control R. We can take a look at the updated imagery. And I'll put the cities back on here. Boundaries, coastal. There we go. And we can see that that convection is moving into the Southwest Intercadet Network right now. I think I can hear the rain outside. And we can see the forecast from the Waikiki Zone substation from earlier today. Before that cloud band arrived, we have a forecast for it to ramp down very significantly. This is that convection moving in. I will refresh this graphic. Again, this is a live forecasting graphic. And we can see, yes, actually, that ramp down did happen. Very thick, opaque cloud cover conditions out there right now. But look, hold me to it. I'm going to say that it gets brighter later this afternoon after these storms move through, and that's what the forecast is saying. So the question comes down to whether or not I'm right, and we'll give that a go. I'm not afraid to say it. I've done this a couple times now. I've yet to be wrong, so we'll give it a go. Let's see what Collaborator Perfect was able to do with that data. And 29 minutes.
Thanks very much. Yeah, I am guilty as charged. I am a software engineer by trade, but spent a lot of time in the power industry, decision support systems, things that eventually have become the smart grid and data analytics. I don't know, the consultants changed the names for all this stuff, but it's all the same stuff. So lots and lots of data, quite a bit of complexity. I'm probably going to be introducing some jargon today. Unfortunately, it's a necessary evil of the work that we do, and but hopefully the message that we do get across is when you're dealing with volumes of data in the way that we are in this new world of sensors and just massive amounts of data, you do need some slightly updated structures and methodologies to be able to process this into a human consumable format. So what I'll do is my talk is split into two parts. Yep. Again, my talk is split into two sections. One is an explanation of the technology, the components that make up how we've approached this problem, and the second part is actually a live demo that we've recorded as a video, so we can play around with the passage of time. So I'm guessing most people have heard the term big data, and this was just massively overhyped about 5 or so years ago. It was very challenging for mere mortals to wrap their head around. It was the domain of the Googles and the Facebooks and the IBMs and very large organisations. And now what we're seeing is it's become approachable to the point where we can actually collaborate. We can use this technology to add value to most businesses. So what we're finding, obviously, the theory has always been there. You know, from Galileo, Aristotle, Bayes in 1700, he developed a Bayes theory that machine learning models are built on today. It still exists. It's still relevant. Then the human race had a bit of a crack at sort of turning this into numerical computational models in the 70s. Massively expensive Cray computers like the Pawsey Institute. We had one when I was at university in the capital city. You had to post off your jobs to run. If they didn't work, it was kind of bad luck. Send them, try again the next month or whenever you were able to get some time. And so really not an ideal agile learning experience, and certainly not very cost effective. So fast forward, I reckon really Perfect have been at this for about 3 years, and 3 years ago it was pretty hard actually to deal with big data. But I think just in the last 3 years, these tools that we will collectively call big data and big compute, if you like, have really, I think, been able to be operationalised and are outside of the realm of the massive use cases of Google and Facebook that everyone likes to talk about, and now are approachable for a real network. So the other thing is cloud. So like it or lump it, it is, you can spin up huge amounts of infrastructure to do analytics projects very quickly, relatively cheaply. If you leave them on for too long, people do find that the costs blow up, but it's a very good way to get started on a hypothesis and to test something. And then, if you want to go and operationalize it into your IT infrastructure, push it back into standard IT, absolutely, that's fine. So they're just, and this is not to have a go at the ICT infrastructure people, but it's highly available and it's mission critical. So going and poking around in it and doing pilot projects and analytics projects is frowned upon generally. It's not something that people like to, it's been built over time to keep the lights on it, literally. And it is challenging to re-architect. And it's also hard, we find it's not unique to Western Power, it's very hard to scale down to the sort of pilot innovation level. It's just it can be quite expensive. So what that means, unfortunately, the result of that is that you need a big ROI, return on investment, to go through the pain of doing all of that with monster IT infrastructure. But what we're going to introduce today is scalable from very small use cases to very large use cases, and obviously using cloud. So we can rapidly model hypotheses, this whole fast fail notion that's crept into our language, and it's cost effective. You can have it as a service, you can run it for a month or two, switch it off, switch it back on again. It's not an onerous process to do that, not in terms of cost or time. It's quite quick. So what this then does is low barrier to entry. Now we've heard today that solar probably is a problem, so it maybe would attract some investment, but some other use cases maybe not necessarily so. But having a more agile approach, I think, makes a bit more sense. So I do need to probably just step into a little bit of jargon here, unfortunately. So anyone heard of Hadoop? A couple of people. Okay, so Hadoop is a data platform, really. So it's a file system. It's got its own set of databases and data processing engines, and and they're completely different to how things used to work in the past. And the point of this is that it's parallel scalability, both in terms of compute and storage, is effectively limitless. And then you talk about, can you imagine your Facebooks and Googles, how much data they get? It's just phenomenal. So they actually needed to invent a new paradigm, and that's Hadoop. Okay, Hadoop was gifted to the world as an open source project, but that's probably, it'd be a little bit unfair to people go, oh great, I'll grab the open source and I'll just go and build my own Hadoop framework. It's very complicated. So people like Hortonworks and Cloudera, these are just commercial entities, they have taken this world of Hadoop and made it a supported commercial product. So, so that's basically what we would use as our Hadoop platform, is a commercial supported framework where all the bits and pieces, the components talk to each other, it works. Now this is only on version 2.6, it only Hortonworks only started a few years back. So, but it's now stable, it's mature, we can run production workloads, it's all, yeah, it's happy. Now, next bit is the data engineering tool. So it's really not the case anymore that you can just grab a comma-separated file, have a look at it in Excel, and Bob's your auntie, you run a bit of a macro over it. It's not going to work. You're talking billions and billions of records across huge data sets, lots of complexity. It's just not going to happen, right? So you need to be able to orchestrate this data in this big data framework in a human readable and understandable manner. So we'll show that during the demonstration. So it's a simple graphical drag and drop type tool, and it talks Hadoop. So if you wanted to, we had probably a 3-year learning curve to get our head around Hadoop in our engineering team. So we can now deploy jobs in sort of 4 to 6 weeks kind of framework, but it did take us a lot of time to get there, and I don't think we would have got there quite as quickly without tools like Pentaho, which is what we use there to do that orchestration and data engineering. And the last bit of the puzzle is cloud infrastructure. So being able to spin up 100 compute nodes, in a matter of a couple of hours, run huge jobs, scale them back down again, just as impossible in standard hardware infrastructure. So we've got this highly functional, fully integrated data and analytics platform, and we can certainly have quite good results out of that. So again, this is probably the most, I suppose, technical jargon slide in the whole deck, but I do need to show you what it means to a company like Western Power, where we would grab data sources. So not to sort of put any sort of say anything about the Soulcast project. It's highly significant, but it's a data source into our number crunching thing. So we also grab SCADA data from Waikiki only in this case, but that's just for the trial. And then climate data, thanks Josh for that. So these are our data sources that come into our cluster via Pentaho and allow us to run machine learning models to produce results. So we see another couple of little words up there called Spark. So Spark is a parallel in-memory processing engine. Think huge number crunching. Machine learning, unfortunately, machine learning is basically forecasting, predicting, correlating. It's all that kind of AI precursor, if you like, is all collectively called machine learning. And so we're able to then run these big machine learning models on the cluster and leverage this big data, big compute capability to get things done in minutes rather than years of compute. This is very don't try this at home stuff. I try to run this model on my laptop and it froze and ran out of RAM and died like instantly. So it does need some of this this other infrastructure. So what I wanted to highlight here, yes, we're doing Soulcast. It is the most wonderful project I've worked on for ages. But if you swap out those data sets and swap in other data sets, you've got a kind of a common framework to do data analytics. And also the other thing, you can BYO data set, BYO machine learning model, and all of this complexity of the big data layer is really removed from your, doesn't create a barrier for you. So we like to call this kind of co-created solutions or analytics as a service. So we're not saying we would do this for you, we're saying we're doing it with you. So we would start off with the data engineering. We've got specialists in that respect. We shape it, we put it in these clusters, we clean it up, and then we get a subject matter expert who tells us, oh, that's very interesting, I want to look at that. And then, together, then we build some machine learning models, some dashboards, we correlate some data together, and then it goes into operations to solve a business problem, actually for real. The change management required to actually get the value from the data really needs to be done. If you just stop at sort of the third box, that's it, $0 saved. So you've got to push it through the organisation. I think, Grant, you kind of mentioned that a little bit. It does need operations to be on board and believe in it and want to actually effect that change for it to actually be of any value. Just briefly then, Pentaho data integration. I want you to focus on the graphic in there. It's basically, instead of writing software code, which I don't like doing anymore, I used to a few years ago, and some people do, and it's just horses for courses. But when you're a business analyst, you're an engineer, and that's not what your focus is. Your focus is fixing a network problem. You don't actually want to muck around writing code. So we can actually have technical people and operational people staring at this workflow palette and pulling data sets in to something as big as a Hadoop cluster, running jobs on it without writing a single line of code. So it's got this out-of-the-box connectivity to a lot of different data sources, from simple flat files, still very popular, to SQL databases, and of course then to Hadoop. So this library of pre-built components just acts like a flowchart. And it obviously it integrates with all the new platforms, Hadoop, and also the machine learning languages as well. I will introduce one more piece of jargon because it is relevant to real time. So when you've got 140 zone substations streaming stuff in via Pi or directly, you've got loads of stuff coming in from Solcast, weather, and who knows where else. You've got a bit of a problem, a bottlenecking kind of, yet you need to kind of get the data in somehow. It's really non-trivial. So what this component of Hadoop called Kafka does, it acts like a message queue. So you pump data in as much as you like using these things called producers into the Kafka server, and then it's kind of this concertina, this data concertina that spits out stuff on the other side as you need it, things called consumers. So you pump data in with producers, you rip them out using consumers, and that bit in the middle, that flexible message queue can be terabytes. It's huge, right? So you need that in really big data applications. You can imagine Facebook as well. Post, I'm walking down the corridor, I'm going for a coffee, endless streaming in. They do need to do something like this, and that's Kafka. Next one, Spark. I briefly mentioned Spark. So think of if you're running stuff on your laptop, so that thing I just mentioned runs out of puff pretty quickly if you're trying to do machine learning. Much better to run it across 100 nodes and do bits of slice up the job across these 100 nodes, get the answer, and then move on. So that Spark actually runs the job on the actual cluster itself. We're going for time, that's okay. And also I just want to, for the kind of the new machine learning junkies, I just want to highlight the fact that this Pentaho product actually includes 12 classifiers and regressors out of the box. So you don't actually need to write a line of code. You can actually use the defaults, which actually do bring in Weka, Python, R, and Spark functionality, and you can use the defaults and it does a pretty good job, but if you're an expert, you can go and fiddle around with the settings and completely change the way that the algorithm operates. Definitely something worth playing around with. Now, I want to show you what we're going to demo, so that, because it does actually, you need to kind of strap yourself in a little bit. There's quite a lot going on in it. So I wanted to just explain what we're doing, and then I'll show you, and then we can talk about it afterwards. So we don't need to say anything more about why we're doing this. Grant and Nick have done a great job. But I did want to, don't know if you're any Game of Thrones fans, but I wanted to point out what happened on the 19th of October 2017. The first bit of the chart, have I got a cursor? Yeah, look at this. So that dark blue is solar PV actuals from Nick. And then on the 21st, it's obviously cloudy. On the 19th, it's quite a mild day, sub 25. This one, it was slightly hotter. Now, this is classic duck curve stuff, right? So you've got megawatt load of Waikiki Zone substation. Sorry, I should have mentioned, this is Waikiki Zone substation, the main substation, going to 1.3 megawatts at midday, right? It's really quite a drop-off. And at the same time coincident with the peak. And here, it doesn't even go below, I have my glasses on, but it's pretty normal, right? So, as we know, when you've got very low, I suppose, base load power on your zone substation and you're feeding in tons and tons of PV, you end up with major power factor degradation because the phase of the solar can be different from the other one, and you end up with these huge VAR kind of variations. And here, that power factor of the T1 circuit of Waikiki actually went 0, and it did get reverse flows for 45 minutes, the T1. T2 didn't. That stayed positive, and T3 was missing. So I don't know. But anyway, and there's a bit of that going on. That gets into the data cleansing problem and being able to handle what happens. So negative effects of low power factor, increased voltage drop being a big one if you've got long lines. So potential harm to equipment, particularly older equipment that doesn't have good power factor correction. And it is actually expensive to correct. If it became a problem and Western Power said, look, sorry about this, but we've got a bit of an issue here with solar PV, and one of the problems is that we need to introduce better power factor correction, there would be it would be substantial, I think, the capital investment required. So not trying to be alarmist, but this really did happen on the 19th. And because of the increase in penetration, as Nick's saying, it's exponential, then we think in October 2018, so in 5 months' time, the whole zone will go negative. It's quite likely by the looks of that projection. And I don't know whether that's happened before. I don't know if that's a problem. I'm not saying it is, but it's probably something that people just need to be aware of. This kind of analytics platform gives you that visibility. So what we'll see in the demo is Waikiki zone substation data, pretty much only. There are 144, I think, zones, and so if we got data from all of those, we'd have probably, for a few years, 144 million records. That's fine, no problem at all, plus all of the other stuff. So it gets up to hundreds and hundreds of millions of records pretty quickly. And you have to crunch most of it, so you can't just take a slice out of it because that doesn't actually tell you anything. So so we've got megawatt load from 2008 to 2018, 5-minute samples, Solcast solar PV estimates, again 10 years, 30-minute resolution. We've got some of the LV transformer voltage stuff, plus more importantly the power factor and the VARs. And we got Mandurah climate data thanks to Josh, also 10 years. So it's amazing. 10 years ago, this just wasn't a problem at all. It was like no solar, unity power factor. It was all just squeaky clean, all the graphs. But now it's a bit more ragged, that's for sure. We'll take you through a little bit of the Hortonworks stuff. I probably won't labour this too much because we're not here to do a Hadoop seminar. It's more about the result. And then but the data engineering I think is significant because we don't want engineers in particular. Engineers and analysts are pretty much who we want to excite about this. We don't want them to, so this is doing my head in. I don't even want to go there because the data engineering tools actually simplify all of this, so it makes it approachable. So I will spend a bit more time on that. So and then of course you have to display pretty pictures. Of course, that's what everyone wants to see. So we've got a Google Map integration of the PV actual. You can size things so that you can drill in and look at things. And when you look at something, you'll get this is again 19th of October, my favourite day, as you can probably tell. And then the blue line is the megawatt load, and the grey area is the Solcast actuals. And then what we did, just and we're not forecasters, we're software engineers. We just put all of the data that we had into a machine learning model called Weka, which is sort of, I'll show it to you so you'll see what it is, but it basically produces a forecast, and we produced a forecast of megawatt load. So in the hands of experts, I think we'll probably do a much better job, and we just literally mucked around with it for a couple of days and produced that. But we're not selling our forecasting capability. It's more of a component of things that experts can play with or not play with, to actually use to produce good forecasts using all of this data. All right, so.
Just tap the screen. It should.
All right, well, we did practice this one. How did we go? All right, so this is the lead up on the 19th of October. You can see as the PV power goes up, the megawatt load goes down, power factor caves in quite seriously in the middle of the day, and our forecast is kind of, it tracks reasonably well. So this here is the fruit of an enormous amount of computational and data engineering labour underneath. So this is something that an operational person can consume, can understand, but we also want to show you how we got there. Okay, so the majority of this presentation actually has some pretty, I think, almost too full-on technical stuff. So first of all, what we need is some infrastructure, and by infrastructure I mean servers and and storage. So we used Amazon in this case, and we produced a 3-node cluster for the purposes of demonstration. There's no problem with scale with Amazon or Hadoop. You can have thousands of them. So we've just got one master, one worker, and one compute node. You can see pretty simply, what's happened, if it's working, if it's on or it's off. You can actually switch it on and switch it off, and that actually controls your cost. We actually don't run it at night just to save a bit of money. And then auto-scaling as well. This is a feature of cloud that you don't get in a standard data center, where we can burst out, auto-scale your nodes to suit the workload. So it's quite a dynamic and quite a good system for that. And sorry, this is quite interesting. Has anyone got the NBN? So have a look at this this speed. So this is just awesome. So 2.6 gigabit link speed in our cluster, and 1.4 upload. So yeah, no speed problems. So it's not quite a 40 gig backplane fiber node switching, but it's not bad. So okay, so what have we got now? We need to configure our Hadoop cluster. So think of Windows control panel, performance monitor. It's a management console for Hadoop, and this it's not trivial, but it actually, you do have visibility into what's happening with the CPU, with the memory, with the network. You're not flying blind as you would be in a true kind of open source solution. Hortonworks and Cloudera are the same. They provide you with these tools to be able to monitor your platform. So a lot of the jargon on the left-hand side will be unfamiliar, I think, to many people, including myself. But that's the world we're in, I'm afraid, with big data. There's a whole new paradigm of names, of databases, of queues, of scheduling systems that apply on a Hadoop cluster that you wouldn't have known about from I suppose, traditional IT. It is just a new way of going about things. So setting up these clusters does take a little bit of, I suppose, skill. By all means, people can get trained up in that sort of thing, but we've actually developed our own engineering capability to do all that for you, take the pain away, and get these use cases up in a matter of a few weeks rather than years and months. So here we see this one, all the components, 27 components. We've got some CSV files, which is actually the Soulcast data. So that's Hadoop. So that's Amazon, that's Hadoop. Now we want to get some data. And we want to get some data from Soulcast. Nick mentioned the API. So we've developed APIs. Actually, we didn't actually really need to write anything. It just happens in Pentaho. So Pentaho is this graphical palette where you can just literally drag and drop workflows onto the design pane and then configure them. So here we're configuring the data to go from Soulcast into Hadoop. So, and then we'll end up with, as you said, if we wanted to grab the data every 15 minutes or when we've got historical data, you configure all that up in this particular part of the solution, which is the data engineering. And you can run things. It's quite easy to use. So it tells you whether things are working, how many things are read, written. You can go and look at the data as it comes along the way. It's fairly user-friendly. It's probably a bit confronting because for the first time you've ever seen it. But once you've kind of seen it 3 or 4 times, you go, oh yeah, I can see, oh, it's stopped there. Okay, I've misconfigured the network. And it's quite simple to actually get results pretty quickly out of this. And, writing things into a Hadoop cluster without a tool like this requires knowledge of Hadoop. And that's just not that common at the moment. I'm sure that will increase. But it makes it very user-friendly. And here you can see, right, yep, we added another CSV file from Soulcast. So the next part of the presentation, I just want to do, this is actually getting the SCADA data in, but that's not you get the point about getting data into Hadoop previously. The main point of this demonstration is not what's going on the right-hand side, it's what's going on the left-hand side. So if you just, this would take all day, but to go through all of these, but we're just flicking through the built-in functionality. So the point I'm trying to make here is that there's so many built-in transformation steps. It understands all sorts of different data types out of the box. You don't need to know about all of these. It can transform them, it can blend them, it can fuse them. It can do all of this data engineering, we want to call it, without writing any code. And when you run the transformations, you can see how many you've got. I think we end up with 800 or something thousand records as well. So you can see the scale's not massive. I mean, let's be honest, but it's certainly beyond an Excel spreadsheet capability. And that's all then going into our Hadoop cluster. And yeah, so the other thing we did was to create some metadata. So we know that you're not got meters at the moment, but if they're coming down, we wanted to demonstrate some streaming analytics. So recall a little while ago, I mentioned Kafka, the producer, the concertina data queue, the consumer. Well, this is a demonstration of Kafka in action. So here we are actually mimicking a metadata network. So they generally send you data in XML. They're just flooding in. So we flood it into our Kafka queue, and then we pull it out of the Kafka queue as a consumer, and we put it into Hadoop for posterity, for post-processing, for doing whatever you like. So you just, and scale, as I said, is not a problem. So you start the producer, you start the consumer, and away you go. So it's just a very brief introduction, I suppose, into what a real-time analytics system with streaming metadata might look like. And we're seeing investments in the hundreds of millions of dollars in traditional infrastructure in metadata applications, and that's just, it's just getting out of hand because they need to store 7 years or something like that, and there's just ridiculous amounts of data. So anyway, here we go. We just chuck it all on our fairly cost-effective Hadoop cluster, and we go back to our management console, and we can see a bit of activity in the Kafka queue, which I suppose just gives us comfort that we've actually managed to do something. So yeah, not everyone wants to do real time. A lot of people want to look back a day, they want to look back a week, fair enough. But when you do actually say, okay, no, this is now a problem. I want this 1 hour look ahead. That's what I need to do to spot a power factor degradation at a particular zone. Then you probably do need real time, and you probably need quite a lot of it if you want to do your whole network. So the next little component here is around job execution. So we are now using Spark. So remember Spark, in-memory, parallel processing, huge volumes of compute. We've got a Weka model. Now Weka is a machine learning tool that was developed at Waikato University. And here you can see we've got the ability to run on the Pentaho server, which is local, or run it down on the cluster using Spark. So I would typically run it Pentaho for debugging purposes and have a look at it, but to do the heavy workloads for the big data sets, you do need to run it down on the cluster. And it's just a selection of a drop-down box. It's really, really quite simple to use. So what this is doing is it's running our Weka model on the megawatt load data to produce that yellow component forecast that you saw in the dashboard. That's what it's actually doing here. So, and then when you run your job, you can see what's happening down in the bottom pane. You know, to be fair, running any decent kind of a job, it does take some time, a few minutes, you know, but it's not the hours and days that you'd probably need to. And it gives you very rich information after those few minutes of execution. But obviously we're here just to introduce some concepts today rather than I suppose get a full appreciation of what a multi-node Spark execution would look like. So, right, now we've done all this fancy stuff in Hadoop, and we've actually run jobs in Hadoop on the cluster. We've created forecasts on the cluster, but it's no good to us there, unfortunately. And Hadoop is not famous for being a place that you can report from or visualize very easily. It really is just that big data platform. So now we need to pull the data off Hadoop, but only select data, results. We want to pull results off Hadoop and put it into Postgres in this case, or an analytics database, SQL, whatever, Oracle, whatever you want, doesn't matter. And then so whatever then you visualize, your favorite visualization tool that you use, you can then you can visualize it using Click, Power BI is popular these days. But the point is that the heavy lifting's already been done, and that the visualization tools don't do heavy lifting. They just simply do not. So you need to actually do this type of thing here. So here we're looking at Weka. So, this is the OLAP cube. So another piece of jargon. Terribly sorry about that, but I just need to introduce this concept because, again, if you've got 1 billion records, and there's no hierarchy, there's no structure, the data points are not connected in any way, you're just going to end up trawling through a monolith of 1 billion records and never ever get anywhere. So we build something that's called a cube, but it's a multi-dimensional view of the data. So a simple one would be a hierarchy of year, month, day, hour, minute, seconds. That's a hierarchy that gives the analysis an idea of how these data points interact. Likewise with PV estimate and megawatt load, they are connected so that the user of the analytics doesn't run too slowly. It's all about making the analysis run extremely quickly. So that when we come down to create our report, we're just selecting the cube, in fact, the data source. We can pull actuals onto the estimated actuals. We'll pick 2018, click on May. Now, bearing in mind, when it's doing this, it's going through hundreds of millions of records. The speed, because we've got this cube, is phenomenal. And if we didn't have it, it'd just be rotating circles for forever and a day. So you do need the data model and you do need the cube. So I think this is, so this is getting the estimated actuals for all zone substations for May the 14th. And you can do trick things, obviously. You can do this in lots of different tools. You can put them on a Google map, size them by color, or plot them by color in terms of their size. Or you can also plot them by magnitude. So what we like doing was to figure out the biggest blobs in this next graphic are the ones that produce the most solar PV. So this is sizing by solar PV output. And because we've only got Waikiki zone substation data for SCADA, guess which one we're going to pick, right? So we'll pick Waikiki, and we'll have a look at our favourite duck curve again. And I just want to, I suppose this is all happening in real time. This is not split up. So we're going to pick 2017, we're going to pick October, we're going to pick the 19th, and we're going to plot it. And can you imagine if you're doing this using traditional tools with billions of records, it'd just take forever, right? So this allows an analyst, an engineer, someone very rapid access to the actual inner workings of a particular issue that they're looking at. So before, I suppose this just looks at the whole of October. There's literally one-to-one correlation. If the historical PV is down, the load is up. It's just always, it doesn't matter what you look at, it's always the case. And so it's highly, there's a higher degree of correlation. To answer the thing, so there's 35 megawatts connected to Waikiki, and the peak in summer is like 50. And so really there's a very high ratio of solar PV in there. And yep, just to show a little bit more analytics, we've got the duct curve here. You can pull that up for any zone if we had all the data, any zone substation, any day, and have a look at the duct curve. I think we're about to add power factor, but if I was probably developing a solution like this, I wouldn't expect people to go hunting around. We would just alert, power factor degraded here. So you're running a monster number crunch on power factor across the whole network and start alerting on declines. And then people can go and immediately look at the details and get that data. So that's what a big data analytics solution can give you, is it can give you that real-time visibility or even a look-back visibility, but without you having to go through every single zone substation and stare at things. So yeah, it should be pretty valuable as an analytics tool for things like power factor degradation. So, okay, just as one of the last things I want to show you here is Weka. So machine learning is very topical. There's one way of doing it, which is writing R code, Python code. Another way is using this tool. It's called Weka. It's developed by Waikato University, but it's kind of a GUI based. So yes, there's lots of menu items that I'll probably never get a handle on. But our team, as I said, are not forecasters. Within a matter of a few weeks, we were able to produce the forecast of megawatt load that you're about to see. And I thought that was pretty good of the guys. A model is really just, it just teaches the curve what to do in certain circumstances, like a forecast. Okay, if you've seen the following three values, then probably the next one's going to be like that. That's a model, an algorithm, whatever you want to call it. So yeah, as I said, we're not claiming that this is brilliant or anything, but in the space of a few short weeks, we were able to produce pretty decent forecasts, really. And as I said, in the hands of an expert, this would be, I think, phenomenally powerful. And you can then take the results of this model, as we saw in the demo, and I know there's been a lot going on, and produce what we've got here. So this is an exact repeat of what was at the beginning. So what is going on behind this chart is not like plotting stuff from an Excel curve. There's a huge amount of stuff going on under the hood here, right? And so, but therein lies the beauty of it. We've now produced something of fairly elegant simplicity that a consumer, any user can look at and know exactly what's going on in the network at any particular zone substation. So, as I said, so we spent about probably the last 3 years skilling up on Hadoop. We've got Pentaho as our data orchestration layer. That gives you your rapid application development. And what we're looking for, I suppose, and what we're trying to help out Grant's team with is use cases where you want to look at something for a few months without having a huge CapEx spend, analytics as a service, all the big data, the machine learning, plus obviously, really high value data sources like Solcast being brought into the mix. So that's all from me, and again, apologetic about the amount of jargon, and I hope I haven't bored you all silly, but we're just really trying to bring to your attention the need for a different look at the way data is handled. And that's it. Okay, thanks very much.
Thank you very much, and thank you for your close attention. Yes, we'll just
yes.
hand back the mic. We're just going to now conclude the session with a Q&A session. I probably will stop the WebEx broadcast in a sec as well. So this will be available for you to actually review at your leisure on Western Power's YouTube site later. Thank you very much. I hope this has been useful to you. And now we really want to start the conversation about how do we actually get on top of the solar PV? What are the analytics? You've seen some examples, but there are probably other things that electrical engineers need to be monitoring and looking at. And we really want to understand that well so we can produce the sorts of solutions that you actually need. So thank you.